Hello everyone. Today I'd like to show you a way to view the formula for curvature that you might not have seen before. Now this video will assume that you already have some experience with multivariable calculus, but you might not know what the wedge product is, so let's go ahead and go over that a little bit first. So let's say that we have oops, that's the wrong thing. So let's say that we have a vector over here. And we're going to go ahead and call this vector u. U with a little arrow. And next, we're going to have another vector, which I'll go ahead and put over here. And this one will be called v. Now I've drawn the tail of v at the head of u, and there's a particular reason for that, because I want to discuss what u wedged with a v is. Oh. So let's go ahead and think about that for a second. Well, as it turns out, this wedge over here is actually defined like this. We'll go ahead and draw this. And we're going to form a parallelogram with u and v. And so what we end up getting is, if we fill in the region right here with a certain, orange color. So what we end up getting is an object called a bivector, and I will denote that with the letter B over here and this double arrow on top. So a bivector, basically speaking, I'll put that in here as well. A bivector is considered an oriented plane segment. So let's go ahead and write that down. Oriented plane segment. Segment. Okay, so what does that mean? Well, let's start with, say, vector v again over here. Let's just go ahead and draw that. So vector v is actually considered a part of a line. So you can imagine that this is the line over here that vector v is on. So let's put the label on there again. Now, vector v is not just a line segment, right? Because it has an orientation. The arrow in this case is pointing in this direction. So, I mean, it could point in, of course, either direction along a line, but it's pointing, toward the right in this case. Now, as for the bivector that we seen before, gonna go ahead and draw it again. Let's use the straight line tool. Okay, so we have this bivector. Now what it means is that this bivector is also a part of a plane, right? Because there's all this plane around it, and it's just embedded within that plane. So that's what it means by plane segment. And it also has a certain orientation. In this case, it's clockwise. But we can also imagine a version that's counterclockwise, like so. Like this. So this version of the bivector, as it turns out, is actually counterclockwise. So the orientation is in this direction. So just like a vector within a line can have two different orientations, a bivector within a plane can have two different orientations within of course its plane and the vector within its line. Now this bivector over here we can label as B with the double arrow on top. But this bivector over here, this is actually negative B. So, of course, you might know that if you no, that's not the correct thing. Okay, so if you negate a vector, this is minus V, the orientation of the vector is actually reversed. And it's the same thing, because if you look here, when you go from B to minus B, the orientation of the bivector has been reversed, and the orientation of either clockwise or counterclockwise is shown with the arrows around the bivector. So now I want to go ahead and try drawing the bivector another way. So again, we'll have this over here, and this can be right here. So what I'm doing is I'm actually reversing the order of the vectors in the wedge product. And if you see here, that I can write the V over here, and then I'm going to go ahead and wedge that with the U. But if you look here, this bivector right here is actually the same as minus B because it has the counterclockwise rotation. So this is equal to minus b. So you always have to keep track of the order in which you wedge the two vectors together, because flipping the vectors actually reverses the order. And in fact, that's very important. So let's go ahead and write that as a property. U, and this is equal to minus sign. Yep. And then U wedge, get the red, V. So this is called the anti-commutative property. If you think about regular multiplication, right? Like A times B equals B times A. But for the wedge product, reversing the order in which you multiply, or rather the order of the factors, will actually negate the result. So now let's go ahead and talk about curvature. Now this part, I'm assuming, again, you're already familiar with multivariable calculus. Maybe you've taken a course. I'm just clearing up the wedge product because typically it's not covered in typical vector calculus course. But to start, I'm going to go ahead and write down a formula that you might have seen in such a course. Get the white color here. So the formula is that the magnitude, well, actually I'm going to go ahead and write down the kappa first. So here is the kappa. And we use kappa for curvature. So the curvature is equal to the magnitude of the position. Let me get the yellow color over here. Actually I'm gonna go with the blue, I think. Okay. Pink, yeah. So the magnitude of S prime of t, and S is the position function, so it's got a vector arrow, and then over divided by its magnitude. So let's go ahead and do that. The pink. S prime of t and now what we do is we cross that with the second derivative of position, So S double prime of t. And once again, we divide that by the magnitude of S prime of t. And then close off the magnitude here. And finally, we divide the whole thing by, well, I'm just going to go ahead and copy this. Copy and paste and move this down here. Okay, there we go. Yeah, let's go ahead and clean that up. Okay. So let's go ahead and look at what this formula is really saying here. And as an example, we're going to go ahead and take this and we're going to draw a certain curve in the XY plane. And it's going to look like this. Well, these are just the axes, but the curve itself is going to look something like this. Okay, so you can kind of see the general shape of the curve here. And this curve is what we're going to call S of t. Now, if you remember up here, this S of t is our position function. So if you imagine traveling along this curve, this function would then give you the position that you are at any given point on this curve. So, for example, let's say this is an arrow, a vector, and this is another vector pointing at this particular point. And then another arrow over here pointing there, and maybe like this, and maybe like this. Okay, so we've got an idea of what it looks like to travel along this curve. Now, what we're going to do is we're going to think about how much you're turning when going along this curve. So, for example, let's go ahead and use another color. I haven't used this purple before. Okay. So let's say that you're at this point and this is the circle that hugs the curve the closest at that point. So what we want to do is we want to pick another color again that I haven't used. So here is the tangent vector at that point on the curve. So let's call that T1. And let's say that's another, if we take one more step along this curve, then we end up with a different tangent vector. Let's call that one T2. And now what we really want is the change that this tangent vector experiences with respect to the arc length. And then, of course, we have to take the magnitude because we only care about the size. So how do we arrive at this from that? Well, what you have to imagine is that this ds over here. So let's imagine that this is oh, that's not the correct color. Okay, let's say that this is ds over dt. And I've drawn it a bit long just to see that, of course, it could really be, this is just the speed that you're going along the curve, so it could be anything. So now what we want to do is we want to look at the second derivative, which is this. So this is the first derivative, right? This is just another way of writing s prime of t. But now for the second derivative, we want to go over here. And let's say that the second derivative is going in this direction. And in fact, it's this diagram is getting a bit cluttered, so I'm going to move it down a bit. So here's our first vector. This is s prime. Just write, I won't write the parameter because we can assume. Then what we want after that is the, hang on, let's just, yeah. Okay. So this is the second derivative here. You can think of this as the acceleration. And what we really want to figure out is how perpendicular these two vectors are to each other, right? The perpendicularity between the first derivative and the second derivative, because s double prime is telling s prime how much to turn at that point on the curve. So let's go ahead and use a different color here for, all right, yeah. This is salmon. And we'll do that. Okay. So what I've drawn here is the parallelogram that is spanned by these two vectors. And the area of this parallelogram, didn't intend to do that. The area, and I'll write it in the same color as, okay. The area is equal to magnitude of the cross product of these two vectors. And then S double prime over here. And we'll close off the magnitude as well. I forgot to write the vector arrows there. I hope you'll forgive me. So let's think about what the cross product really is again. If you imagine this cross product, it's actually represented by an arrow that's no, I don't want to do that. That's pointing. Well, you have to imagine it pointing out of the screen. But the magnitude of the vector, this arrow here, is represented by the area of this parallelogram. So this is the first kind of strange thing, right? Where we want to think about a parallelogram, but we're representing it with an arrow that's not even in the plane of the parallelogram. So what this gives us an indication to do is maybe we should represent this with something different. So let's see what happens if we represent this with a wedge product. Cross, and then double prime here. Okay, so now this oh, my apologies, I wrote a cross again. Let me just go ahead and get rid of that. Okay, we can go ahead and go over here. Oh, yeah, like that. Okay. Oh, that's not what I wanted. Let's do this. Yeah. Yeah, there we go. Okay. And let's reset that. And we'll go ahead and write the cross, or the wedge. I keep saying cross. Okay. So now what happens is actually this wedge product here actually directly represents this parallelogram because it's really a bivector. And the magnitude of a bivector is actually given by its, sorry, the area of a bivector is actually given by its magnitude, so that those two are equal. So this is actually equal to that area. And so this is a good sign, right? We have this parallelogram that we wanted to think about, and we were representing it with a cross product. But using the wedge product, we can actually think directly of that parallelogram instead of a different vector that's pointing perpendicularly. So let's go ahead and actually try calculating some of this out. And we'll see another potential issue arise with the cross product. So let's say that S of t equals x of t times I hat plus y of t times j hat. Okay, so this is pretty simple, right? We're just expressing s of t in terms of its components. I hat, of course, is the unit vector in the x direction, and j hat is the unit vector in the y direction. Okay, so remember what we wanted to do was take the cross product of these two vectors. So let's go ahead and write that down here. S prime, and then cross S double prime. And what that's equal to is, if we write out the components, we have x x prime of t over here, and then y prime of t down here. And then we're going to go ahead and cross that with x double prime of t and y double prime of t. Okay, so now this is another thing that should maybe be raising some alarm bells, because how are we using the cross product if it's supposed to be only work in 3 dimensions, but the vectors here are 2-dimensional? Right, so there's a bit of a mismatch. Right, this is 2D, but the cross product is only supposed to work in 3D. And this goes back to this diagram right here, where we had this arrow that you have to imagine is pointing out of the screen, like toward you. We're dealing with a problem in only 2 dimensions, but we have to invoke a 3rd dimension just for the cross product to make sense. Now, you can calculate this. Of course, what you have to do is take the diagonals, right? Like this, and like this. And that would be equal to x prime and then y double prime. Let's go ahead and write that here. Minus y prime, it looks like an x, y prime x double prime. Okay. So what's really going on here is that actually we're actually assuming a third dimension in this calculation, because let's imagine that you put a 0 down here and then a 0 down here. That would then make these vectors exist in a three-dimensional space. But it's kind of a hacky workaround, right? So what if we wanted to do this without having to arbitrarily invoke this third dimension? Well, as it turns out, the wedge product has got you covered. So let's go ahead and see what the wedge product looks like in this context. So again, we have S prime. And then we have to wedge that with S double prime. And what we're going to do is actually express this in terms of the addition form. So let's do that. So this is X prime of T times I hat plus Y prime of T times J hat. And you can imagine how this would happen, right? Because if we take the derivative of the whole vector, that's the same as taking the derivative of the terms of the sum. That's just the sum rule. And now let's go ahead and wedge that with, well, I'm out of space over there, so I'm going to write it down below. X double prime, let's not write the parameter, we can assume that, I hat plus Y double prime of J hat. Okay, so now that we have it written in this form, we can actually do a bit of the distributive property. Because as it turns out, the wedge product acts like normal multiplication in terms of the distributive property. So let's go ahead and write each of these terms down. And we'll just go ahead and distribute it out. So let's write another equals down here. Oh, I wanted to write an equals. Okay. So X prime times I hat. Now this is what we're going to be wedging with X double prime of I. So let's go ahead and wedge that. X double prime I hat and then plus X prime I hat wedge with Y prime J hat, or Y double prime J hat, excuse me. let's see. Plus okay, we're running out of room here. Y prime j hat. So let's do that. And then wedge with x double prime I hat plus final term y prime times j hat wedged with y double prime j hat. Okay. So now we can just compute each of these terms individually. So first let's think about this term right here. And in fact, if we go all the way back up, we can kind of see what the general shape of these vectors are. So let's say that this is x prime times I hat. And then this is x double prime times I hat. Okay, so now how do we take the wedge product of these two? Well, the answer is you have to look at the parallelogram that these two span. But as it turns out, since they're pointing in the same direction, there isn't really a parallelogram here. So what we say is, in this case, that the wedge product of these two vectors is 0. And now if you repeat similar logic for y prime j hat wedge y double prime j hat, these two vectors are also parallel. They're points in the y direction. So both of these are also 0. So already we've just eliminated two of the terms, and now we just have to worry about these two. Now, if you look at x prime times I hat wedge y double prime times j hat, let's go ahead and redraw that. Redraw the x over here, and then go ahead and draw. It's like it's pointing about there. So if we look at the wedge product between these two, we can actually see that there's this region within. And this is a bivector, which is actually a rectangle, because I hat and j hat are perpendicular to each other. So of course they, scaled versions would also be perpendicular to each other. And let's also think of this y prime j hat wedge x double prime I hat as well. So actually what we can do is, if you remember from earlier that the wedge product is anti-commutative, what we can do is we can swap these terms. So let's go ahead and take this, copy and paste. Then clean up some bits over here. Okay. So this is actually then equal to, that's minus x double prime of I hat wedge with y prime of j hat. And because these are just scalars, we can actually just factor them out. So this is equal to minus x double prime y prime, and then this remaining part is just I hat that was weird wedge j hat. Okay, so now if we look up here again, we were working with this x prime I hat wedge y double prime j hat thing again. So let's go ahead and write that down as well. Rather, let's go ahead and factor the scalars out of the vectors. So, so x prime I hat wedge y double prime j hat equals x prime y double prime I hat wedge j hat. Okay, so now if we look here and up here, these are actually this the same factor of I hat wedge j hat appears in both of these. So what we can do is add these together, because originally we were adding these two terms together. So let's go ahead and do that. So we need this blue x double prime y prime minus x prime y double prime times I hat wedge j hat. And you can see here that if you were to distribute this, oh, actually we need parentheses. Okay, so if you were to distribute this into each of these terms, then we would just get these two results up here. Oh, I swapped around the signs. Okay, there we go. Now it's correct. And this formula might be familiar. Well, usually it's x prime times y double prime minus y prime times x double prime. But we would usually arrive at it by taking the cross product over here, and yeah, exactly like this. So this alternative way of arriving at it, as you can see, it was perhaps more intuitive than having to take the cross product, and it didn't force us to invoke some third dimension. So let's go ahead and see what the magnitude of this would be, because if you remember, what the whole thing we were trying to do was take the magnitude of this bivector over here, which is a parallelogram. So if we go ahead and how about we copy and paste this down. Okay. So let's go ahead and take the magnitude of this. Now, in order to do this, we have to consider the magnitude of I hat wedge j hat first. So let's go ahead and draw I hat and j hat over here. So that's I hat, and then, well, let's draw it at the tip. Then that's j hat. Okay. So what we want is the area of this bivector And you might have already figured this out, but this bivector over here actually has an area of 1. So this right here, this would then have a magnitude of 1. And then we're multiplying it by all of this stuff right here. So 1 times whatever all of this is, then we just get minus x double prime y prime plus x prime y double prime. So we can just go ahead and copy that again. And this is equal to the magnitude of s prime wedged with s double prime. So this is just a certain way of viewing the formula for curvature that you might not have seen before, and it's using something called the wedge product. So just to quickly recap, we think of the wedge product as producing a bivector, right? A bivector. And the magnitude is the same as the area of the parallelogram, which is what we usually get with the cross product, of course. But it works in 2 dimensions. It has a more straightforward geometric picture. And the derivation of the formula, as you can see in this case, was significantly more intuitive. So I was going to do a worked example, but I think this video is running a bit long already. So I think I'm just going to call it here. And thank you for watching.